Welcome back to rates of reaction. We're on to lesson 8 now. Okay, so this is looking at energy and reversible reactions. So the links to the AQA specification for the two different courses are there. Students at the school where I teach, these are the resources available for this lesson. And also the book references are there for you to use as well as the revision guide references you might be using at home. Always like to start each lesson with some pictures, so trying to link pictures to the lesson, and so we'll have a look at these pictures now, and then I'll explain them in a moment. Right, so top left we've got two beakers, one's giving energy. The red one seems to be giving heat out, and then the blue one seems to be taking heat in from that diagram, and there's a reversible reaction symbol in between them. So that will come into what we're looking at shortly. The energy profile diagram, there's the activation energy of the forward reaction, the activation energy of the reverse reaction, and then the delta H, the overall energy change. So delta H is the same, the overall energy change is the same whether you go with the forward reaction or the backward reaction. So an interesting thing to remember just there. The gentleman on the right, Fritz Haber, okay, he was a German scientist during the war, and he was actually involved in making the Haber process as we know it, but also he had links to making poisonous gases during the war as well. Okay, so a little bit of history there. The bottom left, we've got cobalt chloride paper. So this is a special type of paper, as is the anhydrous copper sulfate that we can see in the bottom right that we saw last lesson. But the anhydrous copper sulfate and the cobalt chloride paper, they're both used as tests for water. So the cobalt chloride paper actually goes pink in the presence of water, and the anhydrous copper sulfate we know goes blue in the presence of water because hydrated copper sulfate is blue. So AQA specification, these are the points it wants you to know for reversible reactions and energy. If you are studying a different specification, then just check please with that exam board that everything you need to know is here. If there are other things, you may need to go and find those out. Learning outcomes for today, they're here if you'd like to pause the video and go through those. Alright, what can we remember from topic 5? Topic 5 was energy changes. This is where we did the energy profile diagrams. So what I'd like you to do is draw two energy profile diagrams, one for an endothermic reaction and one for an exothermic reaction. And on those two diagrams, label the reactants, the products, the activation energy, and the overall energy change. So if you pause the video and do that now. If you've got these correct, then well done. So the endothermic reaction, our reactants are at a lower energy than our products, okay? And then the activation energy is going from the reactants to the top of our curve. And then the overall energy change is the distance between the reactants and the products. On the exothermic side, the reactants have more energy than the products. The activation energy is still going from the reactants up to the top of the curve, and then the overall energy change is again between the reactants and the products. So well done if you got those correct. So last lesson we looked at reversible reactions, and one of those examples was hydrated copper sulfate, where we can heat it up to dehydrate it to form anhydrous copper sulfate. So the hydrated copper sulfate was blue and the anhydrous copper sulfate was white. So the formula for hydrated copper sulfate was CuSO4.5H2O. So what do you think the formula for anhydrous copper sulfate is? CuSO4, good. And the second product? was H2O. All right, I then asked you to write a word and symbol balance symbol equation for this reaction as well. So have a go at that. Excellent. Now then, if you remember from last lesson where we looked at reversible reactions, there's a bit of an error on this slide. So in the symbol equation there, we should have 5 lots of water. It should be 5 H2O. All right, so we're going to put those two bits of learning together now. So the learning of endothermic and exothermic reactions, and also what we've done with our copper sulfate and hydrous copper sulfate and the hydrated copper sulfate. So we're going to try and put all of this together. So when water's added to the anhydrous copper sulfate, it turns blue. If we actually held a beaker or a test tube where this was happening, you'd feel it heating up. It'd actually get quite hot. Okay, so what type of reaction do you think this is? Exothermic reaction. Good. It's giving off heat to the surroundings. Okay, remember that's an exothermic reaction. So then, how could we then turn the blue hydrated copper sulfate back into white anhydrous copper sulfate? What did we do last time to go from the blue copper sulfate to the white copper sulfate? So how did we get rid of the water? Heat it up. Good. So if we're heating something up, if we're putting energy into it, what type of reaction takes energy in from the surroundings? An endothermic reaction. Super. So we've just demonstrated, we've just performed that the backward and forward reaction of this reversible reaction, one is heating stuff up, and the other one we need to actually put energy in. Okay, so can you come up with a sentence that actually links the energy changes in the forward and backward reaction of a reversible reaction? Try that now. Good. Hopefully you've come up with a sentence similar to what I've got here. If not, then you need to note this down now. So if a reversible reaction is endothermic in one direction, say the forward direction, it'll be exothermic in the opposite direction, the backward direction. All right. So it's not always going to be the case that the endothermic is forward. Okay, it could be that your forward reaction is exothermic. But whatever the reaction is in one direction, it'll be the opposite in the other direction. So if the forward reaction is exothermic, the backward reaction is endothermic. So the example here, A plus B reacts to give us C and D. The forward reaction here is endothermic. So from our definition at the top there, we know that the backward reaction must therefore be exothermic. If, for example, in this reaction, the forward reaction takes in 900 kilojoules of energy from the surroundings, how much do we think the backward reaction would give out to the surroundings? Have a think about that now. Right, I'm not going to tell you the answer straight away. We'll work through this, but then we'll come up with the answer in a moment. Right, energy cannot be created or destroyed in a chemical reaction, so the energy can't just disappear. And we've established that the amount of energy taken in from the surroundings when the reaction goes in one direction, okay, in a reversible reaction, is going to be exactly the same as the energy transferred to the surroundings when the reaction goes in the opposite direction. So the example I just asked you a moment ago was with our hydrated copper sulfate and anhydrous copper sulfate. Okay, it's endothermic in the forward reaction and exothermic in the backward reaction. We've learnt that if it's endothermic one way, it must be exothermic the other way. Now then, what you can see now is if 900 kilojoules of energy are used in one direction, then 900 kilojoules of energy are used in the opposite direction as well. It's always going to be the same. Now this is just a number that I've made up for this reaction. All right, the actual energy transfer, I don't know what that is. I've just put 900 in there. Again, we're missing that 5 on the 5H2O for that balanced symbol equation there. Okay, at the start of this lesson, I talked briefly about tests for water and how these two things could be used to test for water. So the first one was anhydrous copper sulfate, so our white anhydrous copper sulfate. Okay, when in the presence of water, that will actually turn blue, is the hydrated copper 2 sulfate. And the second one was our cobalt chloride paper. So normal blue cobalt chloride paper will turn pink in the presence of water. Now, sometimes you'll be asked in an exam what will happen, what your observations might be with these reactions. So these would be observations. The color change would be your observations. Okay, and you need to make sure that you know what those color changes are. Thanks again for watching, everybody. That was energy and reversible reactions. We're then moving on to lesson, I think it's lesson 9 after this, which will be equilibrium. Okay, so hopefully you'll tune into that one, and I'll see you again soon.